So now we're actually changing topic quite much from the statistics. It's about actually predicting and validating, and there are several toolboxes that can help you doing this. We have gone through, we have been looking at TensorFlow, scikit-learn, and there is even a nice little cheat sheet for selecting methods when you are using scikit-learn. More or less following this flowchart, we can say if you have more or less data of different categories. So if you have less than 50 samples, they usually say get more data. Well, that's a pity. So that means you mean to measure more. But usually in the images, you have several features that are buzzing around. So hopefully you can get more than 50 samples. If you only have 50 individuals, then it's a harder case. And then it comes to a lot of branchings about categories, predicting quantity, just looking, structures. Sometimes I actually end up, at least for scikit-learn, with this conclusion: tough luck, not so good. But anyway, you have all these methods, and we have seen in when we use them, we need to work with the data in specific ways. And first, we have some inputs that could be images, could be some points or feature vectors, or some kind of multi-dimensional tensor. And output are different kinds. We actually already mentioned them. It could be a value from the regression, a class, a group, or some kind of vector matrix tensor things with higher degree of input. It's also usually a less degree of input. Usually afterwards we have less noise than the original data too. So in all, the output of all these methods is that we have a dimensionality reduction. So a typical problem when you are working with machine learning techniques is overfitting. So overfitting means it's too specialized for a task. So let's create some kind of magic classifier. I'm not saying anything. So this is just a dummy example. So we have this magic classifier. We give it some training. It says that dog is equal to animal, Bob is a person, fish is an animal. And if we use it with these same inputs, we see that, well, if you give it a dog, it tells me that's an animal. It tells, if you give it Bob, then it tells me a person. So it's really, really great. It's 1 out of 1, 2 out of 2, and even 3 out of 3. Now, what happens if we would give it something else, like an octopus? Somehow it tells us that it's an animal. If you give it Dan, it tells me it's a person. Actually, I don't know what happened behind this classifier, but somehow sounds too good to be true somehow. With so little data, and it hasn't seen these categories. So something is strange here. So what we need to do is to do some validation, and then we come back to things that I actually already started introducing in the enhancement lecture with this smoke test. And ideally, we want to split the data into groups called training, validation, and testing. And the analysis then developed on the training data. And during the training, it's iteratively validated against the validation data. And finally, to really see the performance, you're testing it against the testing data. There are different rules how to split the data in different categories. So, and one is, for example, 80-10-10 or 60-20-20 or 60 30-10 or something like that. So you can split the different ratios, but you want most of the data in the training set, because that is the one that gives the solidity of the training model. Then we can see here, we talked about this tree analysis last week. Maybe it's too large and need some pruning, but anyway, to do a qualitative assessment on some data, we can give some basic metrics on the visual feedback. We can compare different expectations from with other approaches independently measured. You can also check if there are artifacts included in the output. Does the shape look correctly? Also, are they distributed as expected? Or if the orientation of features is meaningful? All these are the qualitative measurements or assessments we can make. But for that, we need some a priori information still to do comparisons, in particular for the lower three here. Also, artifacts, they are usually relatively obvious if you see them. So it doesn't look like what you want to see, so that would be the artifact. More quantitative, we can calculate the specific shapes and distributions of different metrics. And for each parameter, we can actually parameter in our algorithms, we can establish a relationship between a parameter of the inputs and the metric we get out. And this is our validation workflow. So let's look at this little workflow that I think I introduced in the third or something. I think it was the third lecture or something, where we have some input images, some parameters. We also have a filter, then we apply a threshold, and then we can do thickness analysis and shape analysis out of that. And for that, we have some, so you can see that the green ones are the inputs, the blue ones are functions, the black squares or rectangles are parameters, and finally the blue are the outputs that we want to get. So let's do a parameter sweep. So let's just try the sensitivity of our method by varying, for example, the threshold. And here is some data that was segmented using this workflow. And you can see that the threshold value produces different volumes. This is cubic micrometers. And you can see that there is a variation. In the beginning here, it's a little bit higher than down here. And that is the influence we can see on this data. A little bit difficult to see how many there are because it's so cluttered here. So another way would be to use a so-called Violin Plot, which is a kind of a categorical histogram plot. So you can see here that the shape is more or less the same for these, but if you go beyond 7,000, then the shape changes, and it's not really the same anymore. Another thing we can look at is the orientation. You can see that the general orientation is positive. Some dropouts towards the negative values, and then there is a lot around the baseline 0. But also here you can see there are some trends in the data, and these trends will tell us if it's good or bad or what we are looking for. These are still just qualitative assessments from these curves. It's good, bad, or whatever. a better way would be to put a metric on it, and then we are talking about sensitivity analysis. And in control system theory, the sensitivity is the ratio between some metric and the parameter that you used to tweak it. This makes sense if you have electrical signals, because you have voltage in, voltage out, easy. Image processing is more difficult because the parameter is maybe be giving in some unit of intensity, and the output that we want to measure is some kind of volume, which is a cubic meter. So that would be the unit we would verify on is volume per intensity, which usually doesn't really make sense. So we have to look for something else. And what we can use for image processing, practical, is looking for the sensitivity as the maximum metric minus the minimum metric divided by the average metric. And that gives us also a pretty good sensitivity, which is unitless and easier to handle, or to interpret. Looking at the object count now and its relation to the real measurements, you can see that the threshold, we have an object count that goes down, 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 down until a threshold around 5,000, and then it goes up again. So in this case, it means that we have some kind of optimum around the threshold 5,000. And this kind of sweep makes it possible then to tune to tune your algorithms. And ideally, you should test this also on several data, a little bit varying varying content, varying noise levels or smoothness, etc., to have a full picture of when does the threshold behave in the right way. Could also be that you have the sensitivity. If you look at the sensitivity in different cases, so here we look at the count, which goes down and up again, while, for example, the anisotropy and the volume, they go in the other direction. So it's a little bit contradicting results. And that is something you have to decide, which is the variable you want to look at. In some cases, actually you have to put some kind of sensitivity interpretation on each value, what you need to have. And then you can see actually that around 5.5, you can see that all of them actually have either a minimum or a maximum. So you have to look into a little bit interpretation of what you see in these plots. But there is a clear local extremum at the same point. The reproducibility is, of course, very important. And there are two things we mean by saying reproducibility. One is on the measurement. So the measurement shouldn't be sensitive to how you arrange your sample. It shouldn't be sensitive to noise. So if there are noise in the input signal, it should produce reasonable results still. And also shouldn't be dependent on exact illumination. That depends a little bit on which technique you're using. In some cases, you anyway normalize the data, and then you have a reference illumination. Other case, you can't do it, and then you may be left out to have this dependence, but ideally you shouldn't. Then for the analysis, we come more into technical details. So the analysis shouldn't be computer system platform dependent. Ideally, you shouldn't have proprietary or in-house algorithms, because they are much more difficult to reproduce by other people. And in particular, the proprietary algorithms you can only say you use that tool, but you don't know what it did. In-house, the solution to that is you publish your algorithms together with the publication, or you can also put them in a repository saying, this is the algorithm I used. The worst thing you can do is for a reproducible analysis is manual clicking and tweaking or copying stuff, because that leads you to a jungle of selections, and that's not really good for someone who wants to reproduce, even yourself, when you want to reproduce the same results. And there are even done repeatability tests with people who click on different items, depending on daytime, mood, whatever, how many images they already clicked, you will have different results, and your analysis shouldn't be depending on that kind of selections. It could be, of course, that you need to crop something, nothing about that, but still, you shouldn't have clicking as a main selection for the segmentation method or things like that. Also, if you need to do filtering, ideally you should use the same filter setting throughout your whole data set. Another thing that is very important is to have a single script, more or less like a recipe, going through the whole analysis, where you can see step by step what is done. And of course, comments are very welcome here. You can split it down into several files, but you have one, say, major script that controls everything. So you could do it something like this in Python. If you run Python from the command line, you can import your analysis script, so something you implemented, and then you call that script with file name, and you set a threshold to it, and then things happen. And this one you could then repeat in a loop or something like that, and run over several files using file masks and so on. But anyway, that you have one script that calls your specific algorithm. Things like that you can also do with MATLAB and ImageJ or R. You just have to define a little bit material here, and then from the command line call ImageJ or the R scripts, or you can even go for, let's see, the MATLAB doesn't show. Yeah, that's the MATLAB, sorry. So you can do things like this also from the command line. And the reason why you want to do it from the command line is that then you can just send it away as a batch script on a larger computer. Of course, you can do it in Jupyter notebooks too, but it's harder to run them remotely than if you would have a Python script like this. Now we switch to something that you have been seeing a lot throughout these lectures. I haven't really gone into the details of what it is, but that's data frames. And usually your workflow is some kind of image analysis, which produces features. And finally, you want to do a presentation of it. So this part we have handled quite a lot already. This part is not yet. This one a little bit. But I will come to that also in a few minutes. So what we want is to bring in the data into some kind of tables. And the reason is, first, we could just go through the traditional programming ways using arrays, having one array per feature, or doing some kind of structs or dictionaries. And the operations we want to perform on this feature data is mostly counting. We want to do statistics, select, filter out different features, maybe do some transformations or visualizations. And doing that the traditional way with arrays or dictionaries is, first of all, very time consuming to do. You have to really implement everything from scratch. You have to define everything. It's also less flexible. And if you start coding things from scratch, the risk of doing some mistakes is relatively high. So instead, you want to work with data frames, which is a data container. So it's kind of a table. You could see it as a code version of a spreadsheet. It's organized into columns and rows, and takes actually any data into the columns. So you could have images in this data frame too, which we did a couple of times actually already. On these data frames, you can apply filters. You can select fractions of it based on one column and get that selection as a new table. You can sort the rows, you can perform arithmetics, you can also compute statistics very easily. And important is also that you have the whole I/O part where you can read and store files and databases. Really getting into the depth of how to work with it, I recommend looking at the pandas documentation, and then there's also this tutorial getting started with pandas. But as a little extract of that, we can look into some things right here. You can create a data frame from a dictionary, from a data file, or from NumPy arrays. The first step you need to do is to import pandas. So that would be calling the line import pandas as PD. I'm not sure if I mentioned it before, but you can, when you do import a library or a module, you can rename it to something that is more convenient. And some of these modules have relatively standardized abbreviations. So pandas is PD, NumPy is NP, matplotlib plotting is PLT, TensorFlow is typically TF, and so on. So there are some more or less a convention that is used throughout how people are using abbreviations for these modules. And if we want to create now a little a table, let's go. Let's just do a data list. It's an empty list first. And we want to create a table with positions and sign values. So we create in that a little dictionary for each row. The dictionary has the entries, position, which is equal to the index of the loop. And it has an item sign, which is the value of the sign of the position. To create, so this would produce a little list. Actually, I can split this one and let's just look at what it looks like. Print DL. So not very nicely plotted, but you can see here that the entries of this list is always small packages like this. These packages are now put into a data frame. So when you create a data frame, you call PD for pandas .data frame, and then you provide this list of small dictionaries. And then we can look at the top of the list, and you can see here now a little bit nicer format than we had above as this table, where you have the position and sign. I have been using other things, like you can also use head, where you specify the number of rows, or you can use tail, that would be taking the last 5, or you can do sample, which I have also been using. Let's take a sample of 5. Then it takes 5 random elements out of the data. So this is a quick way of looking at the data frame. The sample, as you can see here now, is just completely random. So if you want, you can also put here sort. Oh, you couldn't. That was too much assumption, sorry. But there is a sorting function. I can just not right now tell what it is. So these are the options that you have when you just want to take a quick look at your data frame. Another way to get data into a data frame is to read a spreadsheet. So the one format is comma separated values, and that you can call pandas.readcsv. I think there is also read Excel available, so that would actually read an Excel spreadsheet, but then you need to specify which sheet you are looking at before you can import it. And let's look at this. So it's some kind of phenotype table. I actually don't know exactly what these different values correspond to, but you can just take a look at some sample out of it. And you can see that we have 5 rows and 35 columns. And there's, you can see also here, it's so wide that it puts it a shortening here, but it gives you, a little overview. If you want to save it, you can also save the table in the same way. So you can save it as CSV. This can mainly be done if you only have text and numbers in the table. If you have images, I honestly don't know what happens when you start to save it as CSV. So maybe you should avoid that. Or you can try it out, of course. It's also an option. But I don't think it makes much sense to save an image as CSV. So that could be just saved. And let's go on. So now we can start working on columns. So we saw that the table had different columns, and we want to add a new column, and it's very easy to do that with pandas. The only thing is you have to do is you say you have the data frame and you want to create the column cosine, and you say what the cosine is. And in this case, we compute the cosine out of the position. Then you can do another one, which is the sum, which is the sum of 2 columns. So we select actually 2 columns out of the data frame. And finally, we look at what the values are. And you can see here, position, get the sine value, get the cosine value, and we have the sum. So it's very easy to actually add new columns. So if you, for example, would do a segmentation, you could, or clustering, you could add a new column called clusters, and then it tells you which cluster it is for each row in this table. Oops. One thing that is very useful within the data frames is content filtering. So you could, for example, go into a data frame and say you want those rows where the data frame for the sine, or the column for sine, is less than 0 is less than this value. And then we can take a look at the table again, and we see that the sine is now all positive. So that's exactly what we wanted. And then we have another one, is that sometimes we starting setting some column names, and we want to maybe rename them. So we started maybe calling them A and B when we created it. And that's not really useful. Maybe we want to call it something more like sine and cosine. And then we can use this function rename for the data frame, where you say the columns should be called A should be renamed to hey, and B should be renamed to hop, if that makes sense to the content. And then afterwards, you see that the new data frame is like this. An important thing here is to let's see. Is to notice that this is only instantaneous. So if you want to have a data frame that is called like this, then you would actually have to assign it. So you have to reassign. So say df3 is equal to this. Otherwise, it will not stay. That's an important thing to notice. And then we look at df3. So we can also do statistics with the data frames. So it's very easy to compute all these operations. So mean, standard deviation, min, max, median. And here I compute the average values. You can see that position average is 4.5, sign is 0.20, and so on. It also tells us that it's data type 64-bit float. And I have somehow truncated it. That wasn't smart. Happened somewhere along the line. So, and I lost it somehow. Now I got these values, and we can go on. And another thing we can look at is describe, which actually does all these measurements at the same time. So here you get how many items you have for each position. You get the average values, standard deviation, min and max, and also the quantiles, 25, 50, and 75%. This is even more fun if you want to look at different selections. So you can see here now that you want to look at the standard deviation, where the sum is greater than 0. And then you want to look at the sign table. So you're using one column to decide which ones you want to do computation, and then you plot another column. And apparently here the standard deviation is 0.3. So that's a very powerful thing about these data frames. It can be sometimes a little bit confusing how to select and how to work with it, but you will probably get into it and learn how to use them. Another feature beyond also computing all these values is that you can plot directly from these data frames. And the easiest way to plot is just to do df.plot, and then you get all the columns plotted together. Maybe not so nice because the position has a completely different range than the other ones. So in some case, you need some extra scaling to be sure that you get the right values. Oops, let's go on. Hello. It doesn't want to move on. That's strange. You can also do the same kind of selection or similar kind of selection you did before. So you can do the filtering. Or to begin with, you can just plot a single column. You can also do filtering, where you can select which axis, which column is going to be used. Or else you can also do this kind of filtering. So you have a little bit of everything in these plotting possibilities using the columns. And then you can, of course, use different plotting styles. You can say that you want to plot a bar plot or you want to plot a scatter plot. It all depends on what you want to show, as usually when you do plotting. Setup, what time is it now? 45, okay. Yeah, and then you can also, if you have different data frames, you can also combine them and merge them in different ways. For that, you can really, there is a lot of information in the pandas documentation, but some examples you can do is concatenating frames. So that would be taking rows from the two columns and put them together into a single one. And here you, in principle, just create a little list of the frames you want to combine, and then you say concatenate these frames. The result here is that you can see that the row number is inherited from each of these two data frames. So frame 1 had 0 to 3, and frame 2 had also 0 to 3, which doesn't really make sense, because then you would have 2 index 0. So instead, what we can do is we can say that already when we create these data frames, we can tell which index the rows have, like here and here. And then you can do the concatenation. And then you can see that they have a nice long sequence here. Another one is, concatenation does it row-wise. If you do merge, then you can take actually columns and put them on the side of each other. So here we have 2 data frames, one with 4 columns and one with 3 columns. And they are combined together. And you can see here that we get a nice merge in between them. Yep. And you can see also when the index is not really matching, it appears to do something where the ID is maintained. So exact how this merging works is something you have to look up into the manual, because there are usually a lot of tricks and things you have to look into. Then we can create a new data frame out of selected columns. So you can just do with double square brackets. You can select which columns you want to create, and then you can look at the new created table here, which is just an excerpt of the other one. The question is when you should use data frames. So pandas is useful for large data, but the requirement is that you need to fit it into the local memory. Really big data need other options. So for example, there is the Dask data frames, which can work on distributed data and access it in the same way. And how do we work with it in quantitative imaging? When you start with your experiments, you have a very huge data size. That's a raw image. The segmented reduces the size, but still it's pretty much the same. Then you come into feature data. Now you have a higher level of abstraction and also a lot less data. When we go to the statistics, we have very few data points and the level of abstraction is even less. And finally, you come to some model, which is more or less just a few model parameters. Then the level of abstraction is very high and you have very few data to work with. You can store, as I said, images in the data frame, but it's worth to think about, is it really needed to put them in the data frame, or can you work with them in a different way? It can be really big data frames, and the risk is, again, that you go beyond what the local memory really can handle. So that is a little bit of trade-off, how big data you work with. In machine learning, it's very popular to put these images in data frames, in particular small tiles, but the full images, they take a lot of space, in particular if you have 3D data. So maybe you shouldn't put those into the data frame. So the last part for today is about visualization, and it's about presenting your results. You have done the whole processing chain. You have got some statistics, you have got some tables with these statistics in them, and now is the question how to present it. And a little bit depends on how you want to present, in which context you want to present it. And first is only discussions. So you and colleagues, or you and your professor want to discuss the results. Next step is you would do it on a presentation, or even a publication or a thesis. Another category is putting up on a web page. And depending on what you are working with, or which purpose you prepare your data or visualization, you have to maybe do different choices. Oops, it doesn't work somehow. Yeah. There are different purposes. One is really during your own work. Then we're talking about visualization for understanding and exploration. The audience is very small, and you know it. It's you, maybe only you, and also some colleagues. This group of people have a very high understanding of what you're really looking at, and are probably on the same step as you when they look at the data. The other level is a little bit more tricky. It's presenting your results to a wider audience. Sometimes it's even an unknown audience, or maybe in your group. It could be a reader of a paper, or a person listening to your presentation. Different. Here you have a little bit different strategies how to present it. And what you can expect from this kind of audience is that at best, they have a general understanding of what you're talking about. In Knaflic, interesting book about how to present your data. She draw this little sketch here where you have on this curve amount of control you have. So interaction control you have with the presentation, and the level of detail you need to have in your visualization. So if you are doing a live presentation, you can really adapt to questions, you can modify. It's more about you explaining as you go. So here you don't need that much detail. If you have a written document or an email, then it's a completely different thing. And also on a web page, then it's a different thing, because then you have almost no control of how the reader or the audience is perceiving the material. So in that case, you need a high level of detail in your visualization. So there are a lot of bad graphs. So there are pretty many graphs. I've seen them on presentations, in publications, which tells me that the author thinks my data is very complicated. Or the other one is, I know how to use this or that toolbox in Python, MATLAB, or Mathematica, whatever. They're also the thing that most programs you're working with will produce very bad plots by default. And the other thing is, producing a good visualization that really brings your message out takes time to do. XKCD, I got this nice little graph, which actually tells a trend that happened when the PowerPoint and MS Paint came to life. Before that, it was a lot of actually scientific artists who did all the nice plots. And then came PowerPoint, where everybody could do their own illustrations and plots. It was really sometimes really bad plots that came up, not very well thought. You got just the data as it came and without any good material. And then all of a sudden people woke up and said, oh, why should we do this crap? And then the quality of the plots actually started to improve again. Some bad examples, even worse because I have low sampling, but that's another thing. But this plot here, you don't see anything. You see a few of these purple or magenta dots, rings here, but inside you don't see anything. So in this case, they should probably have been playing a little bit more with transparency to make it possible to see in the depth. Here, it looks more or less good in the beginning, but at some point it just clouds out into a big mesh and you don't see anything of this data. So here you should probably look into working with bands of the coverage and have a central line, which would give a better overview. Then we have some networks here, and networks soon can get very complicated and not easy to get an overview in. In this case, you can even see that one is really hiding all the others, and it's also too much data. So probably you have to do some more better categorization in this plot. So how to improve? Some basic ideas how to improve your plots is, first of all, define what is it you want to tell. What is your message? And think about how can the graphic clearly visualize what you want to tell people. Another question is actually, is this graphic really necessary? Does every line or color serve a purpose in this plot, or is it just because you can? So in principle, what you could do is to pretend that ink is very expensive, and if you don't need it, don't use it. So that is some guiding ideas. And then you can read on a little bit more on these two books. And this is actually just a little forum entry or something. And this is a book. So some simple rules. Never use 3D graphics like the one you see here. It's usually misleading because how should you interpret these cones here? Is it the volume? Is it just the height? Is it the area of the top? What is it? So this can be really misleading and leaving people to wonder what is it they really see here. Pie charts, if they're used right, they make sense, but they can be hard to interpret. But if you have, for example, something that is clearly distributed over 100%, you get a quick qualitative view of it, but sometimes it's still a little bit of an art to use pie charts in the right way. Use almost always white as background, not light gray, or even worse, a gradient for the plots at least. If you do 3D visualizations, actually a gradient can give you a better depth feeling. Then also using color palettes, which are adapted to human visual sensitivity. For example, some people are colorblind. People see different, you can see different features in the image by selecting color map. And then you can also use the colors and transparency in a smart way, so you can see overlapping data in a good concept. Then there was developed something called a grammar of graphics. So in principle, grammar, you know from linguistics. So it's a set of rules how to construct and validating a sentence. And there is always a specific a connection between how different components are arranged with each other. That varies with the languages, but there is always, for each language, there is a specific set of rules. So to graphics, you can actually also apply some kind of grammar. And a lot of this is discussed in this book, Grammar of Graphics. And you can, in principle, set up a plot like a sentence, where you have different elements which you compose in a graphically easy way. And so let's look into this little plot here. We have a nice plot with some data, and it should, and normally a plot should contain different elements, and these elements are first of all the data mapping. That didn't turn out well. So the data mapping, where you have a variable 1 which maps to x, a variable 2 mapping to y, and then you have the points that you want to plot, the actual data, but without the framework of the axis and coordinate system, they don't make much sense, or possibly they do. And finally, you have also labels and annotations. Here I have, actually in the previous one, let's see if I can get to that one. In this one, I actually put some extra thought, because I have blue is low and orange is high. And you can see here, you have actually the connection of temperatures by the levels and how you put the colors. So you can even tell stuff that people don't even think about, but it makes natural sense. In this one, that was an older example, actually. There I had it the other way around, but I hope you see the idea about selecting colors that they already give some level information. Then figure decorations, that's a formality actually, in some sense, that you have when you have plots. Always add a legend telling what each curve represents. Labels on each axis telling what information you have, and sometimes also a figure title. If you have a single panel plot, then the title usually is given, for example, in the caption. Or if you have it in the presentation, then you would probably have a title on the top on the slide. So for single panels, it doesn't really make sense to have a title. But if you have multiple panels, which shows different features, then you should actually have a title on top of each one. When you do images, then it's useful also to have a color bar that help the viewer to see what does each color really correspond to in values. How are they organized? Another thing which is very often forgotten is a scale bar telling what is the size of some feature in the image. So that gives you the viewer a mapping. Is this something in the scale of a landscape? So is it kilometers, or is it something in a microscope image? So it's in microns. So that is a very important information. Then we also have color maps, which I have been mentioning already a couple of times, but there is even it's even a science in itself, and there is a paper written quite recently giving you a flow chart how to select which kind of color map you should use. And it starts by asking if it's ordered, yes or no. And then if it's different classes, then you can use divergent, multi-sequential, cyclic. If it's ordered, you can also use a sequential, and so on. You have here a lot of different, it's actually pretty interesting reading this paper. And it gives this flowchart here, it gives you a good overview. So important is, now we come to a little example, and this is actually going towards the end of today's lecture. So you can ask yourself, what is my message? So let's just plot something to show the results or get a feeling is usually not really good, because all of a sudden these plots, they land somewhere where they shouldn't be. On presentations, in publications, maybe your boss takes it, brings it on to someone else, and without the correct interpretation that you want to give it, you don't get the right response afterwards. And so what we could do, same information, more or less, but now I'm using this Ggplot toolbox, which is working with this kind of grammar in how to present the plot or build up the plot. So what you do here is you have a data frame. You tell us how to map the different variables in the data frame. Here you say you want to plot with points. Here you say you want to have some kind of trend line. And on top of that, you get some labels. And finally, just saying which kind of color theme you want to use and the font size. So this is really divided into these different elements of the plot. And you can even do it in a further way. You can do a scatter plot. So here you do geometric plots, geometric points instead. So this is different data actually. Here I got some kind of random data, and you put some linear combination of it, plus some extra randomization. Now we get again the geometric points, but as you can see here, it's so crowded, you don't see anything. So one alternative you could do is to change the alpha of the points. And if you run that, you see all of a sudden a much better view that where it's getting denser and not. This can be taken even further, that you bin local regions. So you subdivide the data into smaller, is in a coarser grid, and in each grid you compute the number of points in it. And you can see here that you even got this color bar, and you can see the count instead. Instead, in the other one, you could only see by the grayscale from the alpha values. And here you took it into really more quantitative information. You say how many there are in each dot. This can be taken even more abstract, doing contour lines, saying we have different types. This is maybe taking it a little bit too far, but still, this is a way. We could even, let's see. You can also combine it with points if you like. So this is ways you can really improve your plots, and Ggplot gives you this kind of modification possibilities relatively easy. You add points and you add different features. What I've been using a lot throughout these lectures is Matplotlib, where you can do all this, but sometimes it's less accessible, but you can still do it. Plotly is another alternative. Seaborn, you have also seen, for example, the pair plots are from Seaborn. For Matplotlib, if you continue using Matplotlib, I really recommend using this Matplotlib cookbook, where you have the whole book is full of, you want this, here is how you can do it. It's very helpful. So I recommend you to take a look at that one. Ggplot that we looked at right now is a library that actually is based on a library in the language R, but it's ported to Python. So as you saw, we can do it here. And if you want to get a little overview of each of these packages, there is a nice summary on this webpage here. And that brings me to the end of today. And what we have been talking about is statistics. Some of it to be honest, I'm not really a statistician, and this is not a statistics course, but it gives you a little bit a hint on what to think about, that you need many experiments to be able to get some hypothesis testing running. And a good thing is that at ETH, you have free consultations with the statistics from the statistics department. You can follow this link and get information. Problem is, usually you come with too little data and you need to collect more and more and more to get really good statistical conclusions. Sometimes you can use simulations to understand and work with the data to begin with, but in the end, you need to go to the real data. Data frames is something very useful, and you probably in your projects will use them. I recommend it actually. And visualization, you never get around it. At some point, you will have to plot something, and it's better to do it in a good way. Maybe not beautiful, but informative and good, that brings out your message. And yeah, that was all for today. And well, thank you for listening.